Hey, this is Horner, and we're going to take a look at magnetic flux first. Magnetic flux is just a really interesting kind of thing. So let's say that I have a wire here that's in a coil, and imagine that this is the front and then it's going to the back. And then I have some magnetic field lines, and they're all passing straight through that wire. So kind of like if you had a ring and you had some water, and that water was passing through the ring. So it's actually going through the hole. So magnetic flux is really just the product of the magnetic field and area, and it can be thought of as just a total magnetic effect on a coil of wire of a given area. So it's very similar to if you had that ring in the water is going to pass through, and that water might do some weird kind of turning and things, and it might affect that coil itself for that ring. So let's take a look at it a little bit better. For us to have maximum flux, we have to make sure that the area, so what we can do is we can actually shade this in. So if you think about this area here being shaded in and make it more of a flat disk, then we could take take an arrow or a vector and make it perpendicular to that. So it's actually perpendicular to the surface here, and have that arrow stick out. Notice that arrow is pointing in the same direction as the magnetic field itself, and that's where we get maximum flux. So the value for what we call flux will be at its largest. If we go to the next slide, you'll see that this is minimum flux, and now there is no lines that are actually going through that circle. They're either passing above or they're passing below, one of the two, but they're not actually going through the circle, and so we see that that A line now is perpendicular to that magnetic field, and that's going to be pretty important here when we start using the equation. So for the next part, this one is just intermediate flux, so notice it's at a 45-degree angle, so it's neither truly perpendicular nor is it truly parallel. It is just right in between, and we have varying degrees of this that we can do. And since we said the word degrees, we're going to have to look at an equation that will have some sort of trig function in it to help us figure out how much flux there is. So this is just the Greek letter phi, and so we call this phoebe. If you ever have watched the TV show Friends, I think that should kind of ring a bell. If not, look it up on YouTube. Watch a little bit. She's the tall blonde lady. So anyway, this is magnetic flux, and it's really just the magnetic field times the area of that circle or of the ring that we have, times the cosine of the area between the area or the angle between the area and the magnetic field. And if it's at maximum, we see that we just have this B times A. So this is actually B dot A. And that is how you find the flux for something. So let's actually do a problem with this. Here's that ring again. It's not perpendicular, it's not parallel, so we've got to use the formula for it. So we're going to say here phoebe is equal to B times A times the cosine of the angle. We know that the flux is 250, and notice they've put in a prefix here, milli, so this would be 250 times 10 to the negative third, and then the unit is called a Weber, and it's just WB. That's equal to a 50 millitesla magnetic field, so this is 50 times 10 to the negative third teslas, and now we need to do the area, so that would be pi times r squared times the cosine of 40 degrees. You want to make sure that you are in degrees and not in radians when you do this one. They want to know what is the radius of the loop, and so that's what we're looking for is the r. If you go through and do your math, you should end up with a radius of 1.4 meters. Now, why is this flux thing so important? Well, it's important because if you take a magnetic field and you pass it through a coil and that magnetic field is changing, you can actually induce what we call, we can induce current. We can induce EMF, which will then, if it's hooked up in a circuit, cause current. So induced electric potential is just a system that will respond so to oppose the changes in magnetic flux. And when you do that, it's partially offset by an induced magnetic field whenever possible. We can change the magnetic flux through that wire loop, and it causes current to flow because we do have an induced electric potential. This is because if we change that magnetic flux, it does induce that electric potential, which then in turn makes current flow. So let's kind of see how this actually works. To see how it works, we need to talk about an equation. So this is called Faraday's law. It's very easy to do. So this is our potential, much like you would have potential in a battery, but now we're going to have potential in that wire loop caused by the magnetic field. The negative sign here just is so that you can see that it's opposing the magnetic field that's actually there. And so we do N times the change in the flux. And remember, flux is BA cosine of the angle. So that's typically what you have to put in here. And then we divide that by the amount of time that it takes for that to happen. So really what you're going to learn is how a electric generator is about to work here. And remember we says number loops, phi b is the magnetic flux, and then time is just T. Alrighty, here we go. This first problem says I have a coil of radius just 0.5 meters. It consists of 1,000 loops. So what you would have is you would have a coil of wire that would have 1,000 loops in it. So this would be N is equal to 1,000. It's placed in a magnetic field such as the flux is maximum, so we know that the magnetic field lines have got to be going through this way, and that would be parallel to that normal line with the area. So if we fill in this circle, then we have this, there's our A, and here are our B field lines. The field it starts at 500 and then it goes all the way to 0. So now we know what our change in our magnetic field is. They want to know what is the induced potential in the coil. So how much voltage does it actually produce? So to do that, we're going to say that the absolute value of the potential, so this is supposed to be EMF here, is equal to, and then we're going to do N times the change in the flux all over the change in time. And remember we said earlier that this is actually BA cosine of the angle. So let's go ahead and put in our number N. This will be 1,000. Now we're going to do the change in flux, so that's going to be B times A times the cosine of the angle. And we're going to take all that and divide it by time. Now we know the E is equal to 1,000. And we've got to figure out how do we get this change. So we know the area doesn't change, so the area stays the same. And our change here comes from the change in the magnetic field, since it's going from 500 all the way down to 0, all divided by our change in time. So we also need an equation for area. So here's our 1,000 for our N. Area, remember, is pi r squared. And we're going to multiply that times the change in the magnetic field all over the change in time. All right, here we go. Let's do the absolute value of this. This is going to be 1,000. We know pi is just pi. We have a radius of 0.5, so we need to square that. And then here's our change in magnetic field or change in time. And so because our final is 0 and our original is 500 milliteslas, we need to subtract the two and you get negative 0.5 teslas over 10 milliseconds would be 0.01 seconds. So this is why we're doing absolute value, because we usually, if we go from a high magnetic field to 0, you're going to get a negative value, but we really just want the magnitude here. So if you go through and do all your math, you're going to find out that that induced potential is about 39,000 volts. The more coil you have, the bigger the N number, the bigger the magnetic field, the bigger the change in, the bigger the potential, the bigger the change in that magnetic field. So if it would have started at 1,000 milliteslas, we would have had a lot more of this potential. You'd have double. If you make the time smaller, same thing. If you make the area bigger. So electric generators really have huge area, and they have a lot of coils, and they make that magnetic field change pretty strongly. All right, so let's go ahead and take a look at the next sample problem here. I've got a single coil of radius 0.25 meters and 100 millitesla magnetic field. The flux is at a maximum. At t is equal to 1 second, the field increases at a uniform rate, so it's at 11 seconds as a value of 600. At 11 seconds, the field does stop increasing, so they want to know what is the potential at 0.5, 3, and at 12 seconds. Probably the best thing to do here first is on the AP test, they might give you a graph. And so here is our graph that we'll take a look at. We know that we start off at 0.1 and we're going to go all the way up to 0.6 Teslas. That's what 100 milli and 600 milli would be in terms of just Teslas. Here we're going to go over to 1 second, and then finally we're going to end up at 11 seconds. We're going to start in we don't really have any change for that little bit of time, and then all of a sudden we get a big change, and it comes up, and then it levels off again. So just a few things that we need to do. One of the things that we need to do is we need to recognize that t is equal to 0.5 seconds. That would be right here. We don't have any slope. And because we don't have any slope at all, we know that we don't have any induced potential because we're not changing the magnetic field. So remember, that's magnetic field in Tesla over a period of time. And if we don't change the magnetic field, it doesn't matter what our coil looks like. As long as our coil doesn't change size, that magnetic field doesn't change, we won't get any potential. If you look at 12 seconds, we also have a flat line, so this is also equal to 0, which makes it pretty easy. The next thing we need to do here is we need to find out, what is the change so that we can find out at 3 seconds what's going on. So 3 seconds would be here. So anytime in between 1 and 11, not including those two, you will have the same rate or the same change in magnetic field. So let's go ahead and do their m value here for slope. That's equal to the change in the magnetic field all over the change in time. And so here we'll just use the values that were given since that's the easiest thing to do, 0.6 minus 0.1, and we'll divide that by 10 seconds. If you do that, you end up with 0.05 Teslas every second. Let's go ahead and solve for our equation now. So now we have the absolute value of the EMF is equal to N times the change in the flux all over the change in time. So this is equal to the change in BA all over T. We know that A is pi r squared, so this is just going to become pi r squared, and then we'll multiply that times the change in B over the change in T, which we already know is 0.05. So here we go. The EMF is equal to pi times 0.25. That's our radius squared. And we're going to multiply that times our rate, and our rate is right here, which is 0.05. And when we're done, we're going to end up with 0.0098. Notice our units here are meter squared times a Tesla over a second, and that is equal to 0.0098. And remember, we're finding induced potential, so that is just voltage. So that's a pretty easy thing to do. Let's go ahead and check out the next slide here. Next slide is just a demonstration. If you use a generator, you can actually see that flux happening. So we'll have to do that one in class. The next part is Faraday's law of induction. So this is related to what we just did, and this is called Lenz's law. In Lenz's law, we just said the current will flow in a direction so as to oppose the change in flux. So if you have flux going one way, we'll change it in the other. It's kind of like a rubber band. So if I have a rubber band, okay, so here's my rubber band, and let's just say I put a number 2 pencil through it, doop, doop, doop. And if I grab that number 2 pencil with my hand, and then I pull this way, when I make a force go in this direction, then there is a force of the rubber band, or we could call it a spring force, that goes in the other direction. So that's basically kind of what Lenz's law does. If I have a change in the magnetic field, okay, so if I have a change in the magnetic field in this direction, then this rubber band type of thing will help to oppose that change in flux. We can use that in combination with the right-hand rule to predict which way our current will flow. So let's go ahead and try a couple of these. This says I have a magnetic field. It is increasing at a rate of 4 milliteslas per second. They want to know what is the direction of the current in the wire loop. So for this one, the first thing we need to do is say, okay, I see that these dots mean that the magnetic field is coming towards me. So my magnetic field is coming towards me, and it's increasing. If the magnetic field is increasing, if you have an increasing magnetic field in one direction, so we know that it's coming towards us, then there is an induced magnetic field that we're going to call BIND, and it will go in the opposite direction. So if I have an increasing magnetic field that's coming towards me, then there's got to be one that then goes into the page on the inside of this coil. And we call that an induced magnetic field. It'd be similar to if I have rubber bands and the rubber bands are getting stronger coming towards me. To offset that, I have to get a rubber band that will go stronger going the other way. I guess a better, it's not a really great demonstration, but think of it this way. If these are all little tiny water hoses and they're squirting water towards you, in order to oppose those, I would have to squirt water back at them. And that's essentially what's happening in Lenz's law. So now the question is, which direction is the current in the wire loop? So what we'll do here is we're going to take our thumb and we're going to make our thumb go in the direction of the magnetic field. So our thumb is actually going to point into the page. And when that happens, then our fingers will actually then curl around this way. It's a really bad picture, but there we go. Our fingers will curl around to the right, and so we know that the current will go in this direction. So just take your thumb, point it into the page, and you'll notice, and this is for right hand, so remember, right hand rule, don't use your left hand, but your thumb goes in, and then your fingers will curl to the right, okay? Let's try another one and see how it goes. Here it says that the magnetic field is increasing at a rate of 4 milliteslas per second. What is the current direction in the wire loop? Notice this time we have a magnetic field that is increasing into the page. So it is increasing magnetic field into the page. So to offset that, we're going to increase an induced magnetic field coming out of the page. So right here, we're going to have a dot. This is our B induced. And so you take your thumb and you basically point your thumb right at yourself. And when you do that, you see that your fingers will curl around in that direction. So this would be the direction of the current. And this one then would just be counterclockwise. So pretty easy to do there. The next one is actually a qualitative problem as well as a quantitative problem. It says the magnetic field is decreasing. So we haven't talked about this yet. If I have water and it's pointing at me and it's decreasing towards me, then I want to oppose that change. Notice if it's decreasing towards me, it's increasing into the page. And if that's correct, I want to oppose it. So I want to oppose a decrease. And so the opposite of a decrease is an increase. You have to remember that. So now our induced magnetic field here is actually in the same direction. Remember, if I have an increasing magnetic field, then I will have an increasing magnetic field in the opposite direction. Okay, so we'll put opposite. If I have a decreasing magnetic field, then I will then have an increasing magnetic field in the same direction. So this is my induced magnetic field. And it should go in the same direction. So if this one is coming out towards me, we see that my fingers will curl to the left on top. And then if you kind of turn your hand, you'll notice that it curls in this direction. So this is just counterclockwise again. And now we need to go through and do the math. So they want to know magnitude. So we've got to find the magnitude. We've already found counterclockwise, CCW here. We want to find the magnitude. So at this point, we're going to say the induced current is equal to N times the change in the flux all over the change in time, which means that I have one coil, so my number for N is 1. I have area times the change in the magnetic field over the change in time. The area is just pi r squared, and that's times the change in magnetic field all over the change in time. Here we've got pi times, it's a 3-meter loop, so that's squared. And then our magnetic field here is 4 times 10 to the negative third teslas per second, since it's changing at that rate. And it's decreasing, but nonetheless, we're still going to get 0.113 volts. Now, they didn't ask for EMF, they asked for current, and they did give us a resistor. So now we're going to just say that the change in potential is equal to I times R, and so the current is equal to the change in potential all over the resistance. And so now we can just say 0.113 volts divided by 4 ohms, and we get a current of 0.028 amps. And so there's a magnitude, and we know our direction, and that is the end of that problem. We'll go ahead and stop this video, and then we'll go to the last one, which is on motional EMF.